Good day. Welcome to the exida webinar. Today we're going to be talking about Software FMEA HAZOPs. And of course, we'll be talking about doing a Software FMEA or HAZOP with the exida ARCHx tool. My name is Bill Goebel. I'm a co-founder of exida. And as you can see from the bottom of the screen, we're very pleased that we are able to celebrate our 20th year anniversary in the next few weeks. And that has been a real nice, we're real pleased with the growth we've had over the many years. Prior to 20 years at exida, I spent almost 30 years as a new product development manager at an automation manufacturer, and then I did marketing and management. So I've got a lot of background, but the last 20 years have been a lot of fun. exida is a company that has three business groups. We have a group that does engineering tools, things to help all of us do a better job in new product development and certification of new product development. The certification group in the lower right-hand corner uses those tools as part of our work. And then the System Lifecycle Services group provides systems level safety and cybersecurity and alarm management services throughout many industries. exida does a lot of training. Our job is to research, develop methods, and then transfer those methods to the rest of the world to make this place a bit safer. As you can see, we've published many books on the subject. We have many webinars and white papers available on our website. The exida certification group started out in functional safety and now does functional safety in machine, process industry, automotive, vehicles, off-road vehicles, and cybersecurity. We also have a personnel certification program in those areas as well. We only started that in 2004. That's not been 20 years yet. And we were really pleased when ARC Advisory Group did a market study and showed exida was the global leader in functional safety certification. And even in the logic solver category, that's like the safety PLCs, where the whole functional safety certification concepts were started in 1982, exida has become the leader, overcoming a 20-year head start from our competitors. In cybersecurity, exida does automation system, OT, operational technology certification. We pioneered the effort, and to date, people are coming on board pretty rapidly. We are the strong market leader. Talking briefly about our engineering tools group, they have a suite of tools primarily intended for systems level analysis and systems level safety lifecycle services. Many of our customers use those tools. It has the strongest market share globally of any other tool in the world. Finally, the OEM suite of engineering tools is designed for OEM new product development, and it's focused not only on really finding problems and improving design quality, but making projects much easier to get certified. There's been a lot. Everything about the software HAZOP FMEA has to do with engineering process. And you know why. Many of you who are experienced engineering managers understand the need to have a process that improves design quality. We want to reduce design errors, which reduces cost overruns and schedule delay. And of course, when things go really wrong, product recalls and liability. Now, the problem with this is we also want a process that isn't burdensome and bureaucratic and full of unnecessary documentation. So it's tough. But we will work hard on making processes to provide optimal new product development. And it's very clear from IEC 61508 and IEC 62443, that's the cybersecurity standard, that the purpose behind all of the process requirements is to improve the design quality. In 61508, there's a very specific list of requirements that must be met, and those that meet those requirements get a systematic capability rating for a given SIL level. Remember, when I say problems, I mean we want to find errors and omissions. In this webinar today, we're going to use an example process from the exida book, i.e. Functional Safety, and IEC 61508 SIL 3 compliant development process. For those of you who want to dig in much deeper, you're most welcome to get a copy of this book. It's available on Amazon and on the exida.com website. In our particular example process, software architecture design comes after the system architecture design. And we can tell from that we need inputs of the system architecture and the software requirements. The outputs from this step, including both the actual design itself and design verification, which is software criticality analysis and HAZOP. We've lumped these together, and the outputs generated by this merged task is the software architecture drawing, additional design requirements, required test list, and action items that need to be followed to verify product quality. Now, why would we lump these two tasks together? The fact is, if you have a good tool that can be used in a repeatedly iterative manner, you should be doing the HAZOP while you're doing the design. With a tool like ARCHx, you'll be able to go back and forth, and it should speed up the design, believe it or not. We'll be talking about how that could work. As an example project today, we're going to use a simple embedded safety controller. It has 8 discrete inputs, 4 discrete outputs. It has programmable safety functions. It's connected to an external power supply and a number of communication networks so that it can get safety critical variables from peer controllers. And it will communicate to an operator station, an engineering station, and a maintenance station. That's all shown in the context diagram in the lower right portion of your screen. Now, let's say we've done a preliminary software architecture design for the safety critical portion of the controller. And you can see we read local discrete inputs, we execute the safety functions, we write local discrete outputs. We may be also reading peer variables and writing peer variables, sharing safety critical information with other controllers. Our job is to figure out, are there any design mistakes or errors of omission? Well, how do you do that? Let's think about that for just a minute. Many techniques have been developed over the decades to find design problems. These include the classic FMEA, failure mode and effects analysis, the more recent software FMEA, or software HAZOP, and lately even the concept of cybersecurity threat analysis is a similar type of error checking problem-finding procedure. The fundamental steps are pretty easy to understand. We systematically review all the subsystem blocks, basically from bottom up. And that includes hardware blocks, software blocks, FPGA or ASIC functions. For any block, we ask, what can go wrong in that block? Hardware failure modes, software functional failures, or cybersecurity attacks. And after we've identified what can go wrong in each block, we identify, if it's serious, what can be done to verify this cannot happen in a real application, or design an automatic diagnostic to detect the problem and take appropriate action. Or the third thing we could do, one or two or three, is design a measure to automatically correct the problem when it happens. You might be asking, what do you mean automatically correct? Error detection and correction memory. We have a bit failure. The hardware in original ECC designs automatically corrected the problem. Now, when you look at this real common sense procedure with three possible categories of things to do to correct the problem, some years ago, people asked, well, can this even be used for software? And the main objection was, we don't have failure modes for software modules. They're primarily written on a per job basis. There's no standard module with lists of known failure modes. Just forget it. This method cannot be used if I don't have a list of failure modes. Yeah, there were skeptics who were really saying, forget it. And then the HAZOP procedure was created. HAZOPs were first created for the chemical process industry to identify and find mitigation techniques for chemical processing hazards. And of course, many of these chemical process sets of equipment were custom designed, and many of them had no known failure modes. So what had to happen was some new technique needed to be developed. And of course, it is a bottom-up systematic design examination to identify what variations from design intent could occur. And of course, that could apply to software. For every component or every block, we take the attributes and process parameters, and deviations are then examined by using guide words. That's interesting. I didn't say failure modes, I said guide words. We'll come back to that in a minute. Determine possible causes and consequences, specify possible safety measures, and well, obviously we can't do this until the first pass of the design is done. In the world of HAZOP, they had predefined roles, and of course, it is possible to have one person do many of the roles, but most experienced people involved in HAZOPs want at least two people there, a facilitator and a designer, as long as the facilitator is an expert. So it can be, you don't have to have lots of people there, but it is typically done, a HAZOP is typically done in a group. HAZOPs are done with this invention known as a guide word. And there's a whole set of words with the interpretation that was created to help us think of functional failure modes for any given software processing block. And it kind of works, but it's not easy. And sometimes you really have to have really experienced software HAZOP people to use these guide words for software. If we list the basic procedure for a software HAZOP, it is pretty common sense. For every function block, every processing unit, and we call these units, using a set of guide words, we're going to create a list of functional failures. And you remember the text, a deviation from intended functionality. And for each block and functional failure, we list the impact or the effect of that failure on the next higher level subsystem. Then, of course, we need to think about, well, is this important or not? So we list the criticality and severity, if it is a serious problem or a problem serious enough to do something about, and then we list the recommendations and mitigations. That's a software, HAZOP. Well, there's another technique called Software FMEA, and if you start reading the techniques, I'm reading through the steps, you know, they kind of look a lot alike. The big difference I see is in step number 2, and in the Software FMEA, you simply have to create a list of functional failures for each processing block. And I read one well-written textbook which simply said, yeah, brainstorm. Well, free format brainstorming is good. Using a set of guide words to facilitate the brainstorming is probably better. So I started to think, you know, there's not that much difference, but there's still some problems. In the HAZOP, a lot of people complain about getting from a guide word to a functional failure. And yes, it takes experienced experts to really do a good job at that. In the FMEA, people complained about, well, how do I get a list of failure modes for a software module? They're kind of similar complaints. And then, of course, everybody says, what if I miss some of the functional failure modes? Well, what'll happen, of course, you just will have an inferior analysis. Of course, if it's a real serious problem and you miss it, you may deploy the product and discover the problem in the field, which can be very expensive. So missing something is a big deal. Many of the people we've done software HAZOPs with are also thinking, well, how do I know I'm using the best mitigation techniques? And of course, a lot of people say, this is really boring. And boy, I hate documentation. How do I easily document all of this? Do I have to have somebody typing or 2 or 3 people typing during the entire meeting? So they're all issues and potential problems with any of these error checking techniques. Now, introduce ARCHx. ARCHx is an integrated microcomputer architecture analysis tool. It's specifically designed to support finding problems, errors, and errors of omission, and enhance the problem detection methods. And it's a tool designed to help determine if a design meets the requirements of functional safety and cybersecurity. But one thing we wanted to do in order to speed up our own work is use a common methodology for hardware and software and custom ASICs and FPGAs and even cybersecurity. The ARCHx tool has a tree-based hierarchical navigation system for all the different objects. Object-specific editors provide information depending on what type of object you're working with. The project details capture global level information about the entire project for use in automatic and semi-automatic report generation. And those of you who don't like documentation can cheer with me on that one. And the tool can attach reference drawings, figures, and action items as required to supplement and document the activity. But perhaps most importantly, a knowledge base based on the requirements of functional safety and cybersecurity is provided. That will help us do a better job at picking mitigations and making sure our functional failures and failure mode list is more likely to be complete. Now let's look at our three fundamental steps and talk, how do we do this with ARCHx? Well, we review all the blocks. In ARCHx, we call the blocks units. For every unit, we ask what can go wrong with this unit and identify potential problems. We call those deviations. Yeah, it comes from that sentence, deviation from normal operation. Then we identify what can do to verify that it can't happen or put in a diagnostic or correct the problem. We call those mitigations. Then lastly, we answer the questions necessary to show how the design meets functional safety and cybersecurity requirements. Now, how do we do that? Because this is different. This is something that isn't in the traditional software HAZOP, Software FMEA tool set. And what are these requirements? Well, the key is that IEC 61508 requires all software to meet the systematic capability for the target SIL level. And this is an important statement, unless independence can be shown. I read that in the standard and think, what does that mean? Well, and the statement applies to all software, even non-critical, non-safety critical software. And you might be thinking, I've got to meet all those process requirements, even for my non-safety critical software? Well, the answer is yes or no, if you can show independence. Well, what does independence mean? It means, these are fancy words, but spatial or temporal independence. And spatial independence is one element cannot change the data of another element. Temporal independence means one element cannot block or delay another component from running on time without detection. You know how I'd rather word this? Non-safety critical tasks can't prevent the safety tasks from providing protection. To me, that simpler language says it all. The non-safety critical functions, like in our example, configuration, like reporting to the operator station, like reporting to the maintenance station, cannot prevent the safety functions from providing protection. Now let's take a look. The spatial independence. The key here is non-safety critical software tasks cannot change the safety critical data without detection. Well, that kind of makes sense. I mean, you don't want some piece of software with a bad pointer overwriting the data in your discrete input scan. You may very well miss a dangerous condition, which is absolutely not providing the protection function. So there's a number of things you can do. You can have software tasks that run on separate processors. Yes, you heard me. No shared memory, no shared execution. You put in two processors, and sometimes they share a communications bus or a dual port RAM, or sometimes they're completely isolated and simply connect to the same or independent sensors. Memory management units can be used. You can protect the data with means to detect invalid changes. And you can do an analysis showing no memory references are made from one component to another, although that's kind of weak. So there are many mitigation techniques that can be used. We don't know which one to use yet because we haven't established a context. or a cost, or a schedule, and all the other things you do in development. Temporal independence means time, and it's simply the requirement is non-safety critical software tasks cannot prevent real-time execution of the safety critical tasks. There are many things we can do to make sure that is fine, and we can have software tasks running on separate processors. We can use very deterministic scheduling methods and avoid complex multitasking. We can use strict priority-based scheduling. We can use time fences, or we can use a software diagnostic technique where we write a software task that monitors critical execution and critical execution timing, and it's tied to a hardware watchdog timer that can be used to either reset the processor or trip the entire controller to forcing the outputs to go into a safe state. So, how do we use the same methodology for hardware, software, and cybersecurity? Well, we enter all the units, the hardware units, the software units, the FPGA units, the cybersecurity units, everything. For each unit, of course, you may go through different procedures for that with different groups, but for each unit, now this is where ARCHx makes it easy for you. You specify the unit type, and deviations are given to you from the exida knowledge base. Or, of course, you can add new deviations if you have something special that wasn't covered. That helps ensure completeness, consistency, and not missing something. I guess that's completeness. Then you pick the mitigations, but you don't have to pick, you don't have to brainstorm. Mitigations are given to you from the exida knowledge base from a suggested list, or of course, if you come up with even a better solution, you can delete all those and enter your new solution to the problem solving. And lastly, of course, follow-up items are entered into the action item editor as a function of category. Here's a picture of the ARCHx tool where all of the units have been entered. Up at the upper left-hand side, you can see where we've already gone through all the hardware, and we have chosen, we've been given the particular failure modes, and we've chosen mitigation mechanisms. And down at the bottom left-hand side, you can see that we have the software units, and I've clipped them and blown them up so you can really read them, I hope, on the right-hand side of the screen. Software units have been entered. Now, let's focus on what happens next. Let's look at unit E6, read local DI. Well, we're going to call it a software processing unit, which defines a full set of deviations and mitigations. We're going to hit load deviations and hit the load subtree button. Now watch what happens. Boom. For each software unit, ARCHx provides a list of known failure modes and potential mitigations from the exida knowledge base. So for that function, read local DI, you can see now we have 1, 2, 3, 4, 5, 6 well-known failure modes for software. And it looks like we have 3 or 4 potential mitigation mechanisms for most of them. For D89, we're going to put it, we only have one recommended mitigation technique. But all the known failure modes and potential mitigations come from the exida knowledge base. When multiple mitigations are shown, the team may delete any of those not used, or of course, enter new ones. Now we're not saying if there's 4 mitigation, You don't have to use all 4. They're just different ways of solving the problem. Pick the one or more that you think is best for your design. Sometimes when you pick a particular one or delete ones that you're not going to pick, an action item may be needed to follow up to make sure your assumptions have been met. And the tool has an action item editor. In this case, a couple of our mitigations, we're going to delete them because we're assuming that the product is used in de-energized to trip mode. So why do we need an action item? Well, we got to make sure the safety manual or the user documentation states that this product is to be used in a de-energized to trip mode. It's not just a matter of follow through, which is a matter of just good quality practices. When diagnostic mitigations are chosen, the designer has to decide what will happen when the diagnostic detects a deviation. Oh, we didn't think about that. And yeah, you got to. Because a sad story. This afternoon, a project was just about finished. The specifications for a 4 to 20 milliamp transmitter, the safety requirement specification stated that a diagnostic would, when we detect a failure, it would take the output current to a no more value like 3.6 milliamps. It was in the safety requirement specification. It was in the design specification, but somehow during the design process, they forgot about it. Not good. We went to run the final test. We simulated a failure and the current froze, the output froze, for example, and did not go to 3.6 milliamps. Disaster. The whole project is basically shipwrecked. They're going to have to go back and change the design, change the code, go through an entire round of development cycle again. And those of you who are engineering managers in new product development, I can just hear you groan. Oh no. Yeah. Don't forget about the diagnostic mitigation actions. You enter them right here and now, and they go on to an action. They go on to an action list in ARCHx, so that you can verify at the end of the design or the end of the coding that all actions and mitigations have been resolved. That's just one of the features that helps us not only maintain higher design quality, but in the end, based on much less rework, we don't want to increase cost and schedule. ARCHx has a project details screen where we can enter all the rough information, all the detailed information about a project, all the information you need to properly document which project, which version, who's working on it, when was this done, and all the information you need to generate reports that functional safety assessors need to see. I put a lot of emphasis on this ARCHx expert knowledge base. What is it? It's a set of known knowledge, deviation, and mitigations for both safety and cybersecurity that's both context and content specific. So we know what kind of block you're working on, and we'll generate the deviations and mitigations that our experts think are most appropriate. It uses smart renaming, which automatically suggests edits. And when you think about it, it's a significant advance over the traditional HAZOP words because they're specific. And they're specific based on experience with specific functionality. In other words, someone's gone through a whole lot of software HAZOPs and captured all the information and put them into this tool so you don't have to spend as much time brainstorming. And so your list is probably far more complete. Now, the ARCHx tool does include the generic HAZOP keywords, and you can enter them anytime. You can generate a list anytime you want and use them to make certain you've done everything you're supposed to. Now, how does exida get all that knowledge? I mean, think about it. I was in a manufacturing development company for almost 30 years. In that time period, we had two major projects, two generations of a DCS safety PLC, because those are big development projects. And I learned from those two projects, but the advantage of being a certification company with consultants is our specialists are typically involved in 5 to 10 projects a year with all kinds of different requirements and different applications. And a consultant with 10 years of experience has 3 to 10 times the experience of someone in a manufacturing company. And that just gives us a lot of more information to generate this particular knowledge base. In addition, of course, we have many of our people who are very active in the development of both the functional safety and cybersecurity standards. Now, what happens when you're all done? We have a list of design problems and issues. We have a list of mitigation techniques, and they can be in one of 3 categories. We have a list of action items. So we have a list of deviations, mitigations, and the objective of all this is very simple. We want to fix errors and omissions, design errors and omissions of the design at this early design phase, so we don't have to find them during testing, and we certainly don't want to find them during field operation. The part I like the best is perhaps automatic report generation. All the information captured can be extracted using the reports. A whole series of different reports are available. Mitigation measures provide input for the project development team in terms of derived and additional requirements. These same measures show the internal and external certification auditors exactly what's planned and shows exactly how you meet the requirements of the standard with your list of mitigations. The deviation and mitigation measures can be exported into the exida FMEA tool, which saves what information? Well, there's a list of all the units, and at least all the hardware units are applicable. And for each hardware unit, we have a list of functional failure modes. We put those right into the FMEA tool. And when the detailed component level failure mode effect and diagnostic analysis is done, it can be mapped into the functional failure modes, and the functional failure modes for the product can be mapped into the failure modes of the application. And that just saves a lot of transcription errors and quite a few hours of engineering time. Of course, new and custom reports can always be developed. Quite frankly, we put that in for people like me who often want to see something different. Those of you who are experienced engineering managers know that a lot of effort goes into creating design and development procedures to improve your design quality, which should result in a reduced schedule risk and reduced development cost if we reduce the number of design cycles where you have to do work over again. The procedures created by most companies include some good error checking in each step of the process. FMEA, Software FMEA, and Cybersecurity Threat Analysis are really good examples of these error checking steps, and they belong in one or more levels of any process. In general, you could use a spreadsheet for this. There's some inexpensive and even free tools out there. I did an internet search yesterday. But tools like ARCHx decrease the chance for error and hopefully pay for themselves. If you'd like to know more, we have 2 other webinars that have been recorded in the last few weeks using hardware FMEA with the ARCHx tool. And then last week, we recorded a webinar meeting IEC 62443, OEM Cybersecurity Threat Analysis with the ARCHx tool. Feel free to go on our website. They're recorded and available for anybody that would like to listen to them. If you'd still like more information, please look at the exida.com website. We have not only the recorded webinars, but white papers and technical and blogs and technical information. If you still have interest, please don't hesitate to send me an email. The email address is wgobel@exida.com, or look right on the exida.com website. Now, if anybody has any questions, please don't hesitate to either send me that email, or if you'd like, you go right ahead and type up a question right now, and I'll try to answer. We have a few minutes left in our meeting time. I got a question. Can automated unit testing, it says there, yeah, be used to show a problem as a mitigation measure? I'm paraphrasing. To show a problem cannot occur. Well, I really like automated unit testing, especially if it uses the good fundamental techniques of boundary analysis and equivalence partitioning. If it's sufficiently thorough and your analysis indicates that given this set of input vectors to a unit and no faulty output, then it could be used as evidence in a functional safety certification. I have seen it successfully done. It's a bit weak, and probably the assessors would argue with you or make you really prove it somehow, but I have seen it done. Now, I really love the concept of automated testing. It's consistent and relatively inexpensive. Well, to run it, sometimes it's not so cheap to buy the tool. Anyway, I do like the concept, but using it as a mitigation is a weak but possible argument to answer your main question. Can I buy the ARCHx tool with all the databases, or do I buy the knowledge bases separately? That's a good question. The base ARCHx tool is available for sale or lease. It comes with the hardware and software knowledge bases. The FPGA database and the Cyber Threat Analysis database are add-ons because many people just don't have a need for them. But those who want those, they are extra cost add-ons. Good question. Thank you for asking. Well, I don't see any more questions right now. So let me just say thank you all for your time. I hope you found it worth your time. If another question pops into your mind, please don't hesitate to send an email. Thank you very much for attending, and goodbye.